Worked example 19, RLC Phasor diagram. A RLC circuit with the following values of resistance 25 ohms, inductance 100 millihenries and capacitance 150 microfarads is connected to a supply of 300 volts 50 Hz AC. Sketch the phasor diagram for this circuit showing all the voltages and the supply current. So this is the full question, this is the real deal, where you have to calculate the inductive reactance, capacitive reactance, overall reactance, then your impedance, supply current and voltage drops in order to be able to draw the phasor diagram. So let's get started. XL is 2 pi FL, and we're going to have 2 pi times our frequency of 50 times our inductance of 100 times 10 to the minus 3 henries. And that's going to give us an inductive reactance of 31.42 ohms. For our capacitive reactance, we have 1 over 2 pi FC, and that is going to become 1 over 2 pi times the frequency of 50 times our capacitance of 150 times 10 to the minus 6. And that gives us a total reactive capacitance of 21.22 ohms. Our overall reactance X is going to be XL minus XC, so this is going to become 31.42 minus 21.22, and that leaves us with an overall reactance of 10.2 ohms. With this information, we're ready to then calculate our impedance of Z, which is going to be R squared plus X squared, and that's going to give us 25 squared plus the X we just calculated of 10.2 squared root of all, and that gives us a total impedance of 27 ohms. With this information, we're now ready to calculate the supply current IS, which is going to be Vs over Zt, and Vs is 300 volts divided by 27 ohms of impedance, which gives us a supply current of 11.11 amps. At this point, we can also calculate our theta, our phase shift, which is cos inverse R over Z, which is going to be cos inverse of 25 divided by the Z we just worked out previously of 27, and that gives us a phase shift of 22.19 degrees. We can now work out our voltage drops, so VR is going to be IS times R, which is going to be our 11.11 multiplied by a resistance of 25, and that gives us a voltage drop over the resistor of 277.75 volts. Voltage drop over the inductor is going to be IS times XL, and that's going to be 11.11 multiplied by our inductive reactance of 31.42, and that gives us a voltage over the inductor of 349.08 volts. Voltage over the capacitor is going to be the supply current times XC, which is 11.11 multiplied by our capacitive reactance of 21.22, which gives us a voltage over the capacitor of 235.75 volts. With all that information, we can now go ahead and start to sketch the phasor diagram. What I would first of all do, as before, is come up with a scale and then convert each of these into lengths that I'm going to draw on my phasor diagram. And in this case, in the book, I've used a scale of 1 centimeter equals 30 volts, and for the current, 1 centimeter is 1 amp. So just to talk you through what we've done here, 1 centimeter to 1 amp gives us 11.11 centimeters for the current. voltage over the resistor, we take our 277.75 and divide it by 30, and that gives us 9.3 centimeters. 349.08, divide that by 30, and that gives us 11.6. 235.75 divided by 30 gives us 7.9 centimeters, and then lastly 300 divided by 30 gives us a 10 centimeter line. So as a reminder, now that we're drawing the phasor diagram for RLC, we should expect to see our inductor voltage pointing up, our capacitor voltage pointing down, our resistor voltage to the side, and our current here as reference again. Whether the supply voltage points up or down will depend largely on whether or on which of the voltages is bigger. So in this case, the inductive voltage is greater than the capacitive voltage, so that means we're going to end up with an overall upward pointing VS. It's going to point up the way. To draw my phasor diagram, I'm going to need plenty of space here, so I'm going to give myself a nice big axis on the left, and my inductor voltage is going to be 11 centimeters point up the way, and my capacitor voltage is going to be about 8 centimeters pointing down the way. So basically I need to have at least 11 centimeters up for my inductor voltage, and then another 8 centimeters down. So if we go 12 for that axis, and about 8 down, that should be enough space. So for the inductor voltage, VL, we've got 11.6 centimeter line, so 11.6 gives us that. And that's my VL. My resistor voltage, VR, is 9.3. 9.3. VR. My capacitor voltage is 7.9. And my supply voltage is 10 centimeters at 22.19. So unlike the previous two, it's a bit difficult to do the trick with this one because we can't just draw an imaginary cross in space and draw a line to it. So for that, we do need our protractor. So our angle here is 22.2. Or 22, because that's about as close as I'm going to get. So 22 is roughly here. And we need to draw a straight line from there that is 10 centimeters long that intersects the origin. If you're interested in how to make sure draw a straight line through both points, what you can do is if you push your pen onto the page and push your ruler up against that point there, and then keeping pressure at this point so it pivots around it, do the same at the other point and push the ruler up against the pen. And you can do it a few times just to make sure it's fine. Then when you draw your line, it should go through both points, and this one needs to terminate at the 10, which it does. VS for the supply voltage. Lastly, we've got to draw the current, and the current is going to be a line of 11.11 centimeters. 11.1 centimeters IS. Now you'll notice that on here I've just labelled up the vectors with their name. I've not put any angles or values or magnitudes. That's because I've already done that down here. I've given them their magnitudes down here. The angles can be measured off the by drawing with a protractor, and then the lengths can be used and the scale can be used to actually measure off the magnitudes that you've drawn. So that is the phasor diagram there in its whole. I'll put a diagram up on screen so you can see the whole thing. But yeah, that's it.